Mhm. Yeah, so good evening. I welcome to you all to this NPTEL live interaction session. So this week we are going to be conducting the live interaction session of week 4 of the course Advanced Reinforced Concrete Design. So I'm going to turn off my video and I'm going to start today's session. Okay, so I have started sharing my screen. So uh, welcome to this live interaction session of the NPTEL course on Advanced Reinforced Concrete Design. And the course instructor is Professor Surya Prakash from IIT Hyderabad. And presently we are in week 4 of the live interaction session. And this session is presented by me. My name is S. Lalit Sagar. I'm a doctoral candidate and PMR fellow in the Department of Civil Engineering at IIT Delhi. And so this will be the outline or the agenda for today's session. So module 4 consisted of the study on the behavior of reinforced concrete members under pure axial loading. So more specifically, under module 4, we are going to be dealing with the basic laws of mechanics in concrete behavior. And then we are going to study the load displacement behavior of the reinforced concrete members under pure axial compression and tension. Then we're going to be studying about the role of concrete and steel in resisting the axial loads. That is, what percentage of the load is being resisted by the concrete and steel respectively. And finally, we're going to be studying the influence of the behavior of normal and high strength concrete under the axial loads. Okay, so this session is meant to be conducted in an interactive way. So I encourage the participants to actively take part in the discussions. Today we have around 17 questions, most of them numerical, that I have prepared for today's discussion. I encourage them to either unmute themselves and uh, uh, discuss the answer or any doubts that they may have, or they can also type the correct answers in the chat box, because all the questions are in the multiple choice question MCQ format. So with that sort of introduction, I think we can proceed with the today's live interaction session. Okay, so this is the first question. So the load bearing capacity of a reinforced concrete axial member depends on which of the following factors. Okay, so there are totally 6 options. So we need to select all the uh, right options for this particular question. Okay, please take 2 minutes and let me know what is the correct answer. So out of the 6 options, 4 of the options are correct. So let us look at what is the correct answer is. Okay, so the correct answers or options are options A, B, C, and D. Okay, so now let us look at each of the options carefully. So first we have the cross-sectional area of concrete, right? And second, we have the grade of concrete. Third, we have the cross-sectional area of reinforcing steel. Fourth option is the grade of steel. Okay, so the first 4 factors or the options are responsible for the load bearing capacity of a reinforced concrete axial member. Okay, so we can see in the equation which I'm going to present in the next slide also. So this has been taken from the lecture slides. So here the actual load capacity of a reinforced concrete member is given by AC into FC plus AS into FS, where AC is the area of concrete, FC is the stress in concrete, and then AS is the area of reinforcing steel, and FS is the stress in the reinforcing steel. So essentially, these 4 factors contribute to uh, the bearing capacity of the actual reinforced concrete member. On the other hand, the transverse reinforcement. So we have discussed the role of transverse reinforcement in one of our earlier classes also. It is mainly to hold the rebars in a certain position, hold the longitudinal rebars in a certain position, and it is responsible for providing the shear resistance. Okay, not so much the axial resistance. So the cross-sectional area of the transverse reinforcement and the grade of steel that is used are responsible for the shear strength rather than the axial, or that matter even the flexural strength. Okay, so for this question, options A, B, C, D are the correct answers. Okay, so we'll move on to the next question now. So we are going into the numerical problems now. Okay, so consider a square plain concrete column of side 300 millimeter, and the concrete has a mean cylinder strength of 30 MPa. If the length of the column is 1 meter, what would be the force in the column corresponding to concrete strain of 0.001? Okay, kindly take 2 minutes and try to solve the problem and let me know what is the correct answer. So presently we are in the question 2 of this live interaction session. Okay, so we have started solving a numerical problem. So I request the participants to read the question, take a few minutes and let me know what would be the correct response. Okay, so I'm going to start solving the problem along with you. Okay, so we have a square um, axial member. It is having a dimensions of 300 millimeter by 300 millimeter. And it is made of plain concrete. Okay, and the cylinder strength, that is F prime C, is equal to 30 MPa. So we need to determine corresponding to an axial strain of 0.001 that is epsilon c is equal to 0.001. What would be the corresponding column force? Okay, so that is the question. So I think we can have a look at the answer, then we can solve the remaining in the next slide, the rest of the problem in the next slide. Okay, so the correct answer is option D, 2025 kilonewton. Now we have the Hognestad stress strain curve. It is typically used for uh, concretes which have cube strength less than or equal to 40 MPa. That is the normal strength concrete. Now the procedure is corresponding to uh, axial strain of 0.001. Let us find out the value of Fc, that is stress in concrete. So from that we can determine the axial load in the column. Okay. So if anyone is able to solve the answer, you may please type it in the chat box. Okay. Or you can even participate in the discussion. Right. So uh, for normal strength concrete, we'll take F prime C, that is given in the data as, what is F prime C? 30 MPa. Then we have epsilon prime C, that is the strain in concrete corresponding to the peak stress, that is 0.002. Okay. And then we have epsilon C is equal to 0.001. So let us plug these values in the Hognestad relation and let us see what is the value of Fc that we are going to get. Fc is equal to, okay, let me write 30 outside, 2 times 0.001 by 0.002 minus 0.001 by 0.002 square. Okay, so corresponding to this, I'm getting a value of 22.5 MPa. Fc is equal to 22.5 MPa. Okay, so I request the participants to solve the problem along with me, and I also request them to check and verify if they are also getting the same answer. Okay, and once we have the value of Fc, we know that the axial load P is given by Fc into AC plus Fs into As. Okay, we have seen this in the first question already, right? Fc, this one, this particular equation, P is equal to AC into Fc plus As into Fs, right? So here it's a plain concrete column. So Fs or As is not there. So P is given by 22.5 into, what is the area of concrete? 300 square. 300 square by 10 to the power 3, because we are converting from Newton to kilonewton. So solving, we get a value of P is equal to 2025 kilonewton. Okay. It's quite straightforward. Okay, so what we're going to do is basically we are going to take different values of epsilon C, that is strain in concrete, and then we are going to develop this force deformation curve. Okay, so yeah, let us say that This is the force and this is the deformation delta. So we're going to plot this force deformation curve for the shell members. Okay. So I think if we have understood the concept behind this problem, then we can proceed to the next, because right from this particular problem to the final problem, this is going to be the basic concept behind the all the calculations. Okay. So with your yeah, with your consent, I think we can proceed to the next question. Okay. So for the same plain concrete column, we need to determine what is the force in the column corresponding to concrete strains of 0.002 and 0.003. Okay. So I'll start solving the problem. Okay. Uh, the participants may also join me. Go ahead and solve the problem. Okay, so we are taking the same column from question number 2. So in today's interaction session, we're going to be solving the problems on basically three types of columns, right? So in the three types of columns, first we are going to deal with the plain concrete column. Okay, we're going to be dealing with the plain concrete column that will be of having some 4 questions. Then we're going to be dealing with reinforced concrete column of normal strength concrete, and then we are going to be dealing with a reinforced concrete column of high strength concrete. Okay, each of them will have around 3 to 4 questions. Then we are going to plot the force deformation plot for each of these cross sections and compare how the material properties, that is the insertion of the reinforcing steel or the replacement of normal strength concrete with the high strength concrete, how that is going to have an implication on the force deformation curve. Okay, so that will be the essence of today's class. Okay, so I think we can, with that brief outline of today's agenda for today's class, we can proceed with the problem, right? So yeah, we need to determine what is the force in the column corresponding to concrete strains of 0.002 and 0.003. Okay, 002, 0.003. Correspondingly, we need to find out what would be the force or load in the column. Okay, any of the participants are able to solve the problem, I encourage them to solve it and type the answer in the chat box, or they can even unmute themselves and let me know what is the correct answer. Okay, I think I'll go ahead with the solution because we have a lot of numerical problems to cover today. Uh, okay, so I'll show the answer briefly. So the correct answer is 2700 kilonewton and 2025 kilonewton, corresponding to concrete strains of 0.002 and 003. Okay. Now let us solve the problem using the Hognestad stress strain curve or the parabolic curve. Okay, so let me write down the data given. Okay, so what is the data that is given? F prime C is equal to 30 MPa, right? Then epsilon prime C is equal to 0.002. Okay, and then we need to find out Fc for two different values. Fc corresponding to epsilon C is equal to 0.002 and epsilon C is equal to 0.003. Okay, now let us plug these values in this uh, equation and obtain the value of Fc. Okay, so let us look at for a second, let us pause and see this value. So here epsilon C is 0.002 and epsilon prime C is equal to 0.002. So basically the ratio of these two terms is going to be nothing but 1. Okay, which makes the solution very simple. For epsilon C is equal to 0.002. So we have Fc is equal to F prime C, that is 30 into 2 into 1 minus 1 square. Okay, so we can simply write it as 30 MPa. So simply what we are trying to say is that corresponding to when epsilon C is equal to epsilon prime C, the Fc or the stress in concrete is going to be the maximum value. Okay, that is equal to 30 MPa. Now, while we are at it, let us find out the value of Fc for epsilon C is equal to 0.003 also. So we have Fc is equal to 30 into 2 times 0.003 by 0.002 minus 0.003 by 0.002 square, which gives us a value of, I believe, 22.5 MPa. Okay, now to calculate the axial load, I will take another color. It's good. Okay, so we have P is equal to Fc into AC, right? So P1 corresponding to 0.002, yeah, P2 corresponding to strain of 0.003 is equal to 30 into 300 square by 1000, converting from Newton to kilonewton. Then we have 22.5 into 300 square by 1000. Okay, which gives us a value of 2700 kilonewton and 2025 kilonewton. Okay, I hope we are following the problem and the steps to the solution until now. Let us go back to the question slide and mark the correct answer. Yeah, so the correct answer for this particular question is option E. Okay, so we have somewhat assessed the behavior of the plain concrete column under compression. Now let us determine the behavior of the column under tension. Okay. So for the for the square plain concrete column given in question 2, what is the cracking force and deformation under pure tensile loading? Okay. So as we know, plain concrete is very weak in tension. Okay, we need to determine what is the force corresponding to the cracking of the plain concrete column and the deformation under pure tensile loading. Okay, kindly take 1 or 2 minutes and let me know what would be the correct response. So in order to determine both the cracking force and the deformation, we need to follow a rather indirect approach. Okay, we're going to solve it right now. The force can be somewhat attained easily, but in order to attain or obtain the deformation under at corresponding to the cracking load, we need to find out the modulus of elasticity of concrete and so on. So we'll look at the procedure now. Okay. So again, the cross section is the same, right? So our reference cross section is the same, that is plain concrete column having a dimensions of 300 millimeter by 300 millimeter. Millimeter by 300 millimeter, right? We can assume that the tensile capacity of concrete is 10% of the cylinder strength of concrete. Okay, that is Ft is equal to 0.1 into, sorry about that, into 30, which is equal to 3 megapascal. Okay. So from this value of stress, we can easily determine what is the force corresponding to cracking. Again, whether the column is in compression or tension, the basic equation remains the same. P is equal to Fc into Ac for this plain concrete column. So P is equal to 3 into 300 square divided by 10 to the power 3. Sorry. For which we get a value of 470 kilonewton. Okay, so we got that the force corresponding to the cracking in plain concrete is 270 kilonewton. That is option B. Okay. But how do we determine the deformation corresponding to the cracking load? Okay. So for that, we are going to solve the problem further now. Okay, we need to determine what is the strain that is corresponding to this cracking stress. Okay, so we have the modulus of elasticity of concrete is equal to Fc into epsilon c. Okay, so this is for compression. Similarly, for tension, we have Fp by epsilon t. Okay, we know the value of uh, Ft, that is 3 MPa, and we need to determine this value, this particular value, that is epsilon t, and we need to we can somehow find out the value of modulus of elasticity of concrete. So this EC, I'm going to take a different color for better clarity, right? So we have EC is equal to 5000 square root of FCK. Okay, so this FCK is the characteristic strength of concrete, but all we know is the cylinder strength of concrete, that is F prime C is equal to 30 MPa. So from this, we need to obtain the value of FCK. So how do we do that? First, we are going to convert this cylinder strength into the cube strength, that is FCU is equal to 30 into 1.25, that is how much? Excuse me. Good minute. Okay, we have an answer, I believe 37.5. Okay, yeah, thank you for the response. Okay, so I'm all set. FCU is equal to 37.5 MPa. Okay, so we know that if we have the cube strength, this we can take as the target mean strength. So the corresponding characteristic strength would be FCK is equal to FCU minus 1.65 into the standard deviation. Okay, so for this particular grade of concrete, we can safely take the value of standard deviation as 5. Okay, so plugging the value of 37.5 in FCU, we obtain the value of FCK as how much? We get the value of FCK as 29.25 MPa. Okay, so FCK is 29.25 MPa, right? So we can find out the value of uh, elastic modulus of concrete, that is EC is equal to 5000 into square root of 29.25, which gives us a value of, sorry, 27,041.6 MPa. Okay, I'm going to move to the next slide because the slide has become quite cluttered. Okay, so we can obtain the value of the strain in concrete corresponding to cracking. This is given by Fc divided by epsilon c, that is Fc is 3.0, sorry, this is Ft basically, and this has to be epsilon p corresponding to cracking, 3 divided by 27,041.6 which gives us a value of how much? 11.094 into 10 to the power minus 5. Okay, now to find out the value of the actual deformation, we can multiply this epsilon t by the length of the member. Okay, so 11.094 into 10 to the power 5 into 1000 millimeter, which gives us the value of delta as 0.11 mm. Okay, so corresponding to the cracking load of the plain concrete column, cracking load of the plain concrete column is 270 kilonewton, and the deformation corresponding to the cracking is 0.11 millimeter. Okay, so I hope that we have followed the problem until now. Okay, so the next question is related to question numbers 2 to 5. Okay, so the question is to identify the correct load deformation curve for the plain concrete column presented in questions 2 to 4 under compression as well as tension. Okay, so there are 4 options. Just have a look at it and let me know what is the correct answer. So what we did is that I just want to comment or sum up what we did in this particular question. So our aim was, to find out the force deformation curve, right? So what we did was we considered the compressive behavior, and then we considered the different values of strain in concrete 0.001, 0.002, 0.003, and corresponding to 0.004 it is essentially 0. Then for tension, we determined what is the strain corresponding to the cracking. Okay, so for each of these strain values, first we determined the find FC, that is the stress in concrete. Then we determined the force, the load in the column. Then we determined the deformation in the column. Okay, so once we find out the value of the P and delta corresponding to the different values of epsilon C, we generate this force deformation curve. Okay, so yeah, anybody is able to identify which is the correct load deformation curve? So for this deformation delta, so I'm going to take a different color for better clarity. So here we have 1 point over here, 1 point over here, 1 point over here, and here is the cracking, the point corresponding to the tensile cracking. So here we have delta is equal to 1 millimeter. Oh, sorry about that. Delta is 1 millimeter, or epsilon C is 0.001, right? Corresponding to epsilon C is equal to 0.001, we got force of 2025 kilonewton and the deformation was 1 millimeter. Then for strain of 0.002, okay, I'm going to write it here. Epsilon C is 0.002. For a strain of 0.002, we got the load of 2700 kilonewton and the deformation was 2 millimeter. And again, for epsilon C is equal to 0.003, we got the value of P or F is equal to 2025 kilonewton and delta is equal to 3 millimeter. Okay, and finally for this you can take it up as a homework. For epsilon C is equal to 0.004, we get the value of the force or P as 0. Okay, so the plain concrete column reaches its maximum, the ultimate capacity at delta is equal to 4 millimeter. And this here small component of the force deformation plot corresponds to the behavior of the plain concrete column under tension. Okay, so as we can see from this graph, option A is the correct answer, and the remaining I have just scaled the values along the y-axis. Okay, so the correct answer for this particular question, that is the appropriate force deformation or the load deformation curve for questions 2 to 4 is option A. Okay, option A is the right answer. I have basically enlarged the graph from the previous slide. Okay, option A is the correct answer. So let us move on to the next question now. Okay, so after a plain concrete, after dealing with a plain concrete column in the previous 4 questions, now we are going to venture into the reinforced concrete column, okay, having the reinforcement of 4 steel rebars of 25 diameter, and then we are going to determine its behavior corresponding to different concrete strains, and finally plot the force deformation curve. Okay, uh, kindly take 2 minutes and try to solve the problem and let me know what would be the correct answer. So I'm going to start solving the problem by drawing the cross section of the column first. Right. Okay, so we have the outer dimensions of this column is also same as the previous problem, right? So we have a square concrete column. Okay, And then we have four reinforcing bars, each of the rebar having a diameter of 25 millimeter. Then we have the value of F prime C as 30 MPa as in the previous problem. F prime C is equal to 30 MPa, right? And we have Fy is equal to 500 MPa. Now, in this problem, our goal is to determine the value of the axial load or the axial force P corresponding to the compressive strain in concrete of 0.001 and 0.002. Okay, now I'm going to go to the next slide. Okay, the correct answer is option C. Let us take the help of the Hognestad stress strain curve and solve the problem. So now let us try to simplify the problem first. That is epsilon C by epsilon prime C. So for epsilon C is equal to 0.001 is equal to 0.5. Now we have Fc is equal to yeah 30 into 2 into zero point 0.5 minus 0.5 whole square. So this is actually similar to what we got in the previous uh, problem as well with respect to the plain concrete column, that is 22.5 MPa. Okay, now in addition to the stress in concrete, we need to determine the stress in the reinforcing bars. Okay, so Fs is equal to Es into epsilon s. Es is the modulus of elasticity of concrete steel, and epsilon is the strain in the steel, that is 2 into 10 to the power 5 into 0.001, which gives us a value of 200 MPa. Okay, now let us determine the corresponding stresses and strain for epsilon c is equal to 0.002. Okay, for epsilon c is equal to 0.002, we have epsilon c by epsilon prime c is equal to 1. Okay, so as we have discussed earlier, Fc becomes 30 MPa and Fs is equal to Es into epsilon s, that is 2 into 10 to the power 5 into 0.002. So Fs is equal to 400 MPa. So now we know that the axial load capacity, that is P is equal to Fc into Ac plus Fs into As. Okay, this is the governing equation. So we need to determine the values of the area of concrete and the area of steel. Okay, so let me take a different color and try to find out what is Fc and Ac. So let us first find out the value of As. As comprises of 4 steel rebars of 25 millimeter diameter, that is 5 by 4 into 25 square into 4, right? and AC would be 300 square minus AS. So what would that value be? AS is 1963.5 mm square and AC would be 880 3 sorry 036.5 mm square. Okay, so we have all the required values to determine the axial load in the column. So now I'm going to take a different color to write down the answer. Okay, we don't have the space unfortunately. So I'm going to just give you the hint and proceed to write the final answer. Now for a compressive strain of 0.001, we have P is equal to FC, we know that it is 22.5, AC is 88,036 millimeter square, and Fs is 200 MPa, and AS is 1963 mm square. So the force in the column corresponding to this strain is yeah 2373.5 2373.5 kilonewton. And for epsilon c is equal to 0.002, we have Fc is equal to 30 MPa, EC is 88,000, Fs is 400 MPa, and AS is 1963.5 mm square. So when plugging all this equation, we get the value of force as, how much do we get? 3426.5. 3426.5 kilonewton. Okay, let us go back to the answers and let us check the options once again. 2373 and 3426. Yeah, 2373 and 3427. So out of these five options, option C is the correct answer. Okay, we can proceed to the next part of this question. Right, so again, to give you a framework of what we are doing today. So broadly, there are three examples that we have taken, right? We have the plain concrete column, then we have the reinforced concrete column, RC1, which is having a normal strength concrete. Then we are having the second reinforced concrete column, which is made of the high strength concrete. Okay, so we already solved the first problem. So presently, we are in the process of developing the force deformation curve of the second column. Okay, so corresponding to the strain in concrete of 0.001 and 0.002, we obtained the corresponding forces in the column as 2373 kilonewton and 3427 kilonewton. Okay, so we'll proceed to the next part of this second big problem that we have. So for the column that is given in the previous question, okay, that is for a square concrete column, excuse me, okay, for a square concrete column of side 300 millimeter and length 1 meter, that is mentioned in question 6, okay, which is having a mean cylinder strength of 30 MPa and reinforced with 4 steel rebars of 25 millimeter diameter, what would be the force in the column corresponding to the concrete strains of 0.003 and 0.004? Again, assume the value of Fy as 500 MPa. Okay, kindly take 2 to 3 minutes and let me know what would be the correct answer. Okay, I'll be solving the problem along with you. So in order to develop the force deformation curve, we need to capture the behavior of the column under compression and the tension, right? So for compression and tension, and then in compression, we found out we are finding out what would be the force, that is P, and the deformation values corresponding to epsilon c is equal to 0.001, 0.002, 0.003, and 0.004. And correspondingly, we'll find out corresponding to the cracking strain and corresponding to the yield strain of the rebar. Okay, yield strain of the rebar reinforcing steel. Okay, now let us try to get back to the question and solve the problem and get the correct answer. So we have a lot of questions to solve today. So I will go ahead and start the solution part. Okay, we can always come back and discuss if you have any doubts. Okay. Again, because it is a normal strength concrete, we are going to take the help of this Hognestad stress strain curve, right? And we have, okay, epsilon c is equal to 0.003. Okay, and here let us do the calculation for epsilon c is equal to 0.004. Let us simplify the value of epsilon c by epsilon prime c. Okay, I think I need to erase this part. Okay, so what do we get here? 0.003 by 0.002 gives us a value of 1.5, and here epsilon c by epsilon prime c gives us a value of 2. Okay, let us solve the take the help of this equation to arrive at the stress in concrete, that is Fc. Fc is equal to F prime C. Let us take out the 30 outside. 2 into 1.5 minus 1.5 square, okay, which gives us a value of how much? 22.5 MPa. 22.5 MPa, right? And then we need to find out the value of Fs also. Fs is equal to, as I have mentioned earlier, Es into epsilon s. What is the value of epsilon s? Yeah, let us 2 into 10 to the power 5 into 0.003. But if we actually solve the simplify this equation, we get 600 MPa. Okay, but we know that we have assumed a bilinear elastoplastic relation for the steel, right? I'm just going to make it clear using this curve over here, right? So this is known as the material model or the constitutive law that is how the stress and strain are related to each other, or they're interacting with each other. For concrete, we're using this Hognestad stress strain curve for normal strength concrete, which is also called as the parabolic law. But for this reinforcing steel, we know that it will follow, some kind of curve over here and so on. But we're going to idealize the stress strain curve as a bilinear elastoplastic model. Okay, so this will be the strain and this will be the stress. Okay, and here we have the yield stress. Okay, Fy is equal to 500 MPa, and the corresponding strain would be 0.0025. How do we get this strain? It is quite straightforward. We know that by Hooke's law, Es is equal to Fs by epsilon s, right? So uh, epsilon s is given by 500 divided by 2 into 10 to the power 5, which gives us the yield strain of 0.0025. Okay, so yeah, I had taken a small digression to understand, to help us understand what is the model, the constitutive model that we are considering for the reinforcing steel. But now let us get back to this equation. So up to a strain of 0.0025, this equation will hold good. This linear equation holds good. But any strain that is above this value of 0.0025, it takes a value of 500 MPa, right? So it cannot exceed this straight line. So for this particular case of epsilon c is equal to 0.003, we have Fs is equal to 500 MPa. Okay, now let us keep it aside for a minute. And now let us go back to this. Okay, so when you substitute the value of epsilon c is equal to 0.004 or epsilon c by epsilon prime c, as you already discussed, we get the value of Fc as 0. Okay, so the contribution by concrete almost reaches 0, corresponding to this epsilon c is equal to 0.004, and the only contribution is from the reinforcing steel. Okay, so we have the reinforcing steel Fs is equal to, corresponding to 0.004. We know that it has yielded and it is in the plateau region, so the value of Fs is going to be 500 MPa. Okay, now we know that what is the governing equation to determine the axial load in the column, that is P is equal to Fc into Ac plus Fs into As. So what we need to do in order to get the answer for this question is that, corresponding to strain in concrete of 0.003, substitute the value of Fc and Fs, that is 22.5 MPa and 500 MPa, and obtain the value of P. And the value of P that I'm getting is how much? For P it is, yeah, 2962.6. 2962.6 MPa, sorry, kilonewton, and corresponding to a strain of 0.004. Okay, this is the governing equation. Substitute Fc as 0, and then Fs is 500 MPa, and As is, we know we can take it from the previous example. And for that, I'm getting a value of P as how much? 981.75 or 982 kilonewton. Okay. So corresponding to a concrete strain of 0.003, the axial load is 2963 kilonewton, and corresponding to a concrete strain of 0.004, the axial load is 982 kilonewton. Okay, let us go back to the question, the options, and see which is the correct response. Yeah, out of these, option C is the right response. 2963 kilonewton and 982 kilonewton. Okay. So we have captured the compressive behavior. Now let us proceed to uh, understand or determine the behavior of the RC column under tension. Okay. So for the square RC column given in question 6, what is the cracking force and deformation under pure tensile loading? Okay. We need to determine the force and deformation corresponding to the cracking of concrete. Okay. I'll start solving along with you. Okay. Please solve along with me parallelly and let me know what would be the correct response. Okay. Okay, so I'm going to just explain what I have done so far, right? So up until now, procedure has been same to determine the cracking force for the plain concrete column. So first what we did was, let me take the highlighter. Okay, so first we determine the stress corresponding to the cracking in the concrete or its tensile capacity, that is 0.1 into F prime C, that is 3 MPa. Okay, and the corresponding strain, that is epsilon T, is equal to Ft by EC. So how do we find out EC? EC is equal to 5000 root FCK. FCK we can determine from the cylinder compressive strength, that is F prime C into 1.25, which gives us FCU minus 1.65 into the standard deviation. The standard deviation is taken from IS 10262, which gives us a value of FCK of 29.25 MPa. Okay, from this we can determine the value of EC as 27,041.6 MPa, and when we plug it in this equation, we have epsilon T is equal to uh, 3 divided by Ft by EC, that is 11.094 into 10 to the power minus 5. Now let us go to the next slide and solve the remaining problem. Okay, we'll come back to the answer later on. Okay, so we have E is equal to FCT into AC plus Fs into AS, right? We already know that AS is equal to 1963.5 mm square and AC is equal to how much? 88036.5 mm square. Okay. Now we know the value of FCT, we know the value of AC, so we know the value of AS also, but we need to determine the value of Fs. Okay. How do we get the value of Fs? Fs is equal to epsilon S, that is the strain in steel, into the modulus of elasticity of steel. This we do it because of the compatibility of the deformation. Because when you take a reinforced concrete column and subject it to a uniform compression or uniform tension, so the rebar is going to be deforming in the same amount as the concrete. Okay, so this we're going to call it as compatibility of deformation of the concrete and reinforcing steel. So from that we can determine the value of Fs, which is nothing but what is epsilon S? Epsilon S is 11.094, 11.094 into 10 to the power minus 5 into the elastic modulus of steel. So we get the value of Fs as how much? 22 MPa. I have simplified this particular value. Okay, so when we plug it in this equation, let me expand or write out all the equation. FCT is 3 into 88036.5 plus 22 into 1963.5, which gives us the value of how much? Okay, 307.3 kilonewton. and delta is given by epsilon into L, okay, which is, yeah, 11.094 into 10 to the power minus 5 into 1000, that is 0.11 millimeter. That is the value of delta. So the value of P is 307 kilonewton, delta is 0.11, right? So the correct answer would be option C. Okay, let us now move another one step ahead in this big problem of determining the force deformation relation and find out the force and deformation corresponding to the yield point of the reinforcing steel. Okay. Uh, yeah. So essentially, what we're doing is this is the column subjecting it to the tensile force. So first we did corresponding to the cracking of concrete. Now we need to determine corresponding to the yielding of steel. Find out the P and delta values. Okay. So we might have observed that once the initial cracking of the concrete axial member takes place, we are not going to consider the contribution of concrete anymore. Okay. So we have P is equal to Fc into AC plus Fs into As. So Fc, it turns out to be 0, okay, beyond this point, and all the axial load, axial tension is going to be taken up by the reinforcing steel. Okay. Now we have assumed that we are calculating the force corresponding to the yield strain, that is epsilon s is equal to 0.0025 or Fs is equal to 500 MPa. Let us plug these values and find out what is the axial load. 500 into 1963.5, which gives us the value of P as 981.75 kilonewton. Okay. And what would be the corresponding deformation? Delta is given by epsilon into L. Anybody would like to answer? What would be the value of delta? So yeah, it is straightforward. It is nothing but delta delta is equal to 2.5 millimeter. Okay, simple. So the correct answer is option A. Option A is the correct response. Now let us proceed further. So now we have determined the force and the deformation, uh, the value of the force and the deformation of the RC column under compression as well as tension. Now let us go ahead and plot the load deformation curve for the RC column. Okay, so this is how the load deformation curve looks like, right? Okay, so this is how we started out by determining the value of the force and deformation at I'll take a different color now. Yeah, at epsilon c is equal to let us say somewhere here. Yeah, epsilon c is equal to 0.001, right? Then we found out the value corresponding to epsilon c of 0.002, and then somewhere here epsilon 3, yeah, here is 0.003, and finally 0.004. So this curve over here captures the behavior of the RC column under compression. On the other hand, under tension, what happens is initially there is a cracking, then there is a slight drop in the load capacity. It doesn't reach zero exactly. Uh, there's a slight uh, drop in the load capacity. Then, with the increasing tensile load, the resistance increases to a value of minus 2.5 millimeter. Okay, so up to this point, the stress in the rebar keeps on increasing, right? Okay, sorry, keeps on increasing, right? And once the stress reaches this point, that is over here, so the force plateaus. Similarly, the force also, it becomes a horizontal line. Okay, so based on our calculations from question number 6 to question number 9, this is the resulting load deformation curve that we're going to obtain for the given reinforced concrete column. Okay, so with that we have done the second problem as well. Now let us go ahead and solve the final big problem. Yeah, but before that, there is a small comparison between the load deformation curve of the precast column and the reinforced concrete column. And here you can see that insertion of the steel rebars increases the stiffness, the compressive stiffness, the tensile stiffness, and the peak compressive strength, the peak tensile strength, and essentially the behavior is more ductile when compared to the plain concrete column. Okay, which is why providing the reinforcing steel is significant. Uh, you know, uh, in order to enhance the mechanical properties of the concrete systems. Okay, so there is one theoretical question which I encourage the participants to try. So when a plain concrete column is reinforced with steel rebars, which of the following properties of the column does not vary significantly? Okay, please take 1 minute and let me know what would be the correct response. When a plain concrete column is reinforced with steel rebars, which of the following properties does not vary significantly? So here, the option A, we are basically talking about its compressive behavior, right? the post cracking stiffness, the ultimate compressive strength, again the compressive behavior, and then we have the initial cracking load, which is the tensile behavior, and then we have the ultimate tensile capacity. So we have a few more questions to solve for today. I'm going to go ahead and provide the correct answer. Okay, we can always have a discussion later on. So out of these properties, it is option C which is not significantly affected because of the reinforcement. Okay, so here is the explanation. Adding the steel rebars to the plain concrete column significantly influences or increases the axial stiffness. That is the first point. It increases the ultimate compressive strength, and it also increases the ultimate tensile strength. However, the initial cracking load is not much affected by providing the steel rebar. Okay, it is only marginally increased. So we can see this uh, in this slide has been taken from the weekly lecture slides. So here we can see that addition of rebars in the plain concrete column increases the stiffness, the compressive strength, tensile capacity, but the cracking load does not vary significantly. Okay. So we'll move ahead to the final set of problems for today. Okay. So here we are going to uh, navigate from the normal strength concrete to the high strength concrete. Okay. We are navigating from the normal strength concrete to high strength concrete. So I request you all to kindly take a few minutes to read the problem and try to solve the problem and let me know what is the correct answer. Okay. And as usual, I'll be uh, solving the problem simultaneously along with you. So we have the square concrete column, 300 millimeter by 300 millimeter, the same dimensions. And it is reinforced using 4 rebars, right? Having a diameter of 32 millimeter. 32 millimeter rebars. Okay. Now F prime C, F prime C is equal to 65 MPa. Okay, and Fy is equal to 500 MPa. So it is obviously it is a high strength concrete. So we need to take help of the Thorenfeld's equation. Thorenfeld's equation. So what is this? It's a constitutive relation which relates the strain in concrete to the stress in concrete. Okay, and determine what is the force in the column corresponding to concrete strains of 0.001 and 0.002. Okay, no, so now without any further delay, let us go ahead and solve the problem. Okay, so since we are dealing with the high strength concrete, the mechanics of the problem is slightly different, and it is very important for us to understand. Again, the correct answer is option B. We can come back to the answer later on. Now let us start solving the problem, right? So this is the constitutive equation, right? Fc by f prime c is equal to n into epsilon c by epsilon prime c divided by n minus 1 plus epsilon c by epsilon prime c raised to the power n into k. Okay, so we have, let us start solving the problem now. n is equal to n is equal to 0.8 plus FCU by 21.25. Again, please note that this correction has been made by Sir also in his lecture slide, in his weekly presentations. Okay, so it is not FCK, it is FCU, right? We have 0.8 plus, what is FCU? 1.25 into 65, right? We have prime C is 65, so it is multiplied by 1.25, 21.25, which gives us the value of n as how much? Okay, what is the value of n? 4.62. Okay, and yeah, let us find out. For epsilon c less than epsilon prime c, we have k is equal to 1. Okay, so let me write down k is equal to 1 over here. So what else do we need for the constitutive relation? We need to find out the value of epsilon prime c. Okay, so where is epsilon prime c? Yeah. So for epsilon prime c, so to determine the value of epsilon prime c, uh, we need to know know the value of epsilon c. Okay, the modulus of elastic modulus of concrete. Okay, so let us find out the value of epsilon c. Epsilon c is wc power 1.5 into 0.0385 into square root of FCU. Okay, again, please note that it is not FCK, it is FCU. These corrections have been made in the weekly lectures also. Okay, WC is 2400 kg per meter cube, power 1.5 into 0.0385 into square root of, okay, I think 65 into 1.25 is 81.25. Okay, okay, let me write down the value of EC. EC is how much? 40,802.7. 40,802.7 MPa. Right? We have the value of EC now. Now let us find out the value of, okay, epsilon prime C, right? Epsilon prime C is equal to 0.8 into, again, please note that it is FCU, not FCK, right? 81.25 divided by 40,802.7 multiplied by, what is n? 4.62 divided by 3.62. Okay, I know that the calculations are a bit complicated, but I want you to know, just try to follow me so that we can solve the problem together. So upon simplifying, we get the value of epsilon prime c as 0.002. Okay, it is the same as the epsilon prime c which we assumed for the normal strength concrete. Okay, now we need to we have all the values required to determine the value of Fc. Okay, I'll take a different color now and start solving the problem, right? So we have for, yeah, we need to determine the value of fc for two values, that is epsilon c is equal to 0.001 and epsilon c is equal to 0.002. Make use of this equation fc by epsilon prime c. We know epsilon prime c is 65, n is 4.62. We know epsilon prime c is 0.002 and then k is 1. So when I perform the calculation, I get the value of fc as how much? Okay, so I'm getting the value of fc as 41 MPa, right? And when I substitute corresponding to the value of epsilon c is equal to 0.002, right? Upon simplification, we get the value of fc as 65 MPa. Okay, so again, it is similar to what we discussed with respect to the Hognestad relation. When the compressive strain in concrete, okay, is equal to epsilon prime c, okay, the value of fc becomes f prime c. Okay, so for high strength concrete, the value of for epsilon c is equal to epsilon prime c, fc becomes f prime c. Okay, by that, by that concept, we get fc is equal to 65 MPa. Now, we'll go back to the governing equation for the axial members. What is the governing equation for the axial members? Excuse me. P is equal to fc into ac plus fs into as. Right? This is the governing equation. I have determined the value of fc and then the fs is going to be same as in the previous set of problems. Corresponding to epsilon c is equal to 0.001, we have what is fs? Fs is equal to 200 MPa. And for epsilon c is equal to 0.002, fs is how much? 400 MPa. So, and then we can, I request you to determine the value of AC and AS. So AS is, I'm going to calculate here, AS is equal to 5 by 4 into 32 square into 4. AC is equal to 300 square minus AS. So which gives us the value of 3217 mm square and 86,783 mm square. Okay, so I request you to use this equation and find out the corresponding forces. And when I solve these equations, I obtain the value of for epsilon c b. Okay, 0.001 0.002, the value of P that I get are 4201.5 kilonewton, right? And for epsilon c is equal to 0.002, I get the value of P as 6927.7 kilonewton. Okay, so option B is the correct answer. Okay, so we'll pick up the pace and move on to the next question. Okay, um, we have another 5 problems to solve for today. Okay, so I request you to go through the live interaction session once again, and please let me know if there are any doubts through the discussion forum or in the next live interaction session. Okay, so for the same uh, reinforced concrete column, we need to determine the forces corresponding to the strain in concrete of 0.003 and 0.004. Okay, now for epsilon c is equal to, okay, for epsilon c is equal to 0.003 and 0.004, what will be the corresponding load in the column? Okay, so yeah, let us start solving the problem now. So again, we are going to make use of the Thorenfeld's stress strain equation. Okay, and this is the constitutive relation between the strain and stress in concrete, right? And into a value of epsilon c is equal to 0.002, right? We can take the value as 1. But for strains greater than 0.002, we need to determine the value of K using this particular equation. And let us go ahead and find out the value of K now. So that is K is equal to 0.67 plus FCK divided by 77.5. So how do you find out FCK? FCK is equal to 1.25 into 65 minus 1.65 into, okay, so which gives us the value of FCK as how much? Value of FCK is 71.35. Okay, this is the value of FCK. So the value of K becomes 0.67 plus 71.35 divided by 77.5 gives us a value of 1.60. Okay, very important. Now let us try to create different blocks for epsilon c is equal to 0.003 and epsilon c is equal to 0.004. Okay, so our target is to find out the value of fc corresponding to this value, again fs corresponding to this value, fs corresponding to this value, right? And we know that in the bilinear stress strain relation, for any strain beyond 0.0025, so the stress in the rebar has plateaued, so we can write it straight away as 500 MPa for both these cases, right? 500 MPa. Okay, and for these, I encourage you to kindly take the help of this equation, and for strains of 0.003 and 0.004, find out the value of Fc. I'm just going to write down what is the value that I got, right? So for the first case, I am getting the value of Fc as 19.05 MPa, right? Fc is 19.05 MPa. Correspondingly, for 0.004, it is 3.5 MPa. So as we have seen in the normal strength concrete, usually at epsilon c is equal to 0.004, it tends to drop off and become 0. But in the high strength concrete, even at the high strain value, right? So it is able to preserve some of its compressive strength. Okay, so from this, we know what is the governing equation for the axial members. That is, let me take a different color, write down, that is P is equal to Fc into AC plus Fs into As. So when we plug this value in this equation, we know the value of AC and As from the previous problem. So for this, we get the value of P as how much? 3261.7. And for epsilon c is equal to 0.004, we get the value of P as 1912.2 kilonewton. Okay. Kindly practice this at your home later at a later time, and please verify that you're also getting the same answers. Okay, right? So out of these options, option A is the correct answer. Okay, so we'll move ahead very quickly again. Okay, so for the RC column given in question 12, we have to determine the cracking force and deformation under the pure tensile loading. Okay, so again, I will start with the problem without any delay, right? So we have EC is equal to Ft divided by epsilon T, or we have epsilon T is equal to Ft divided by EC. Okay, so we can take this as 0.1 into 65, that is 6.5 MPa. And what is the value of EC that we calculated earlier? Value of EC is 40,802.7. 40,802.7, which gives us the value of ET as how much? Yeah, 15.9 into 10 to the power minus 5. Okay, so let us go back to the governing equation for the axial members, that is given by P is equal to Fc into AC plus Fs into As, right? So Fc is given by 6.5 into what is the value of AC? AC is, we have determined it earlier, it is 86,083, and Fs is epsilon t into ES, right? That would be 15.9 into 10 to the power minus 5 into 2 into 10 to the power 5, right, into AS. AS is 3217 mm square, okay, which gives us the value of P is equal to 666.58 kilonewton. 66.58 kilonewton, and the corresponding deformation would be epsilon into L, right? That is 15.9 into 10 to the power minus 5 into 1000. That gives us a value of 0.16 mm, right? So we see that the correct answer would be option A. Okay, we'll move ahead. Now, what is the force and deformation in the column at the point of yielding of the steel reinforcement? Okay, again, we'll start with the governing equation very quickly. P is equal to Fc into AC plus Fs into As, right? So we know that once the cracking has occurred, we are going to neglect any resistance provided by the concrete, okay? And Fs corresponding to the yield point is 500 MPa multiplied by the area of steel, that is 3217 mm square, right? So the value of P would be 1608.5 kilonewton, and the value of delta would be 2.5 millimeter. Okay, so now let us look at the force deformation plot, right? So yeah, option E is the correct answer, right? So this is the force deformation plot when we're using the high strength concrete. So here it is the comparison of the force deformation curve for the for the plain concrete column, and RC1 corresponds to the reinforced concrete column with the normal strength concrete, and here RC column 2 corresponds to the reinforced concrete column with the high strength concrete. Okay, here you can see for yourself that how the mechanical behavior in terms of the force deformation curve is getting augmented or enhanced because of the improved material properties. Like compared to the plain concrete column, this is the behavior, improvement in the behavior when we use the reinforcing steel, and this is the further improvement when we increase the diameter of the reinforcing bars and we uh, replace the normal strength concrete with the high strength concrete. Okay, so with that we can proceed to the last the final question for today's live interaction session. Okay, so uh, okay, so yes, let us do the problem quickly. For the RC column mentioned in the question 10, the ultimate compressive and tensile strengths are 6928 and 1609 kilonewton. What should be the revised area of concrete and the area of reinforcing steel if the ultimate compressive and tensile strength to be attained are 8000 kilonewton and 1800 kilonewton respectively? Okay, now let us quickly solve the problem together. Okay, so we have PC is equal to PC is equal to, this is the capacity, the load capacity under compression, and this is the load capacity under tension. PC is equal to FC into AC plus Fs into As. Similarly, here also FCT into AC plus FST into AS. Okay. 8,000 into 10 to the power 3 is equal to okay, we are dealing with the peak strength, so it is peak strength is 65 into AC plus uh, yeah, that is 500 into AS, right? Now, the for the tensile capacity, that is 1800 into 10 to the power 3 is equal to, what is the capacity now? Okay, here the contribution of concrete is not considered, so it is simply going to be uh, 500 into AS. Okay, let us call this as equation 1 and equation 2. So by solving these two simultaneous equations, we get the value of AC is equal to 3600 mm square and AS is equal to, oh sorry, AS is 3600 and AC will be 95,384.6 mm square. Now we are going to compare this with the existing AS and the AC values, that is AS is 4 of 32 mm diameter and AC is 300 square minus AS. So when you compare this with the existing values, okay, the value of the area of the steel and concrete to be provided can be expressed as 1.12 AS and 1.10 AC, right? So the correct answer is option B. Okay. So with that, I think we have come to the conclusion of today's live interaction session. So I thank all the participants for joining today. So is there any comment you would like to add? I'll be happy to take now.
Sir, calculator will be allowed for the exam?
Yeah, calculator will be allowed.
Okay.
Yes, yeah. So it will be a multiple choice question based exam. So yeah, similar to what we did today, you can do the calculations in the actual exam as well. Yeah, so I think I'll conclude the session. I thank all the participants for joining, and I look forward to another next week. We're going to be dealing with the flexural members. It will be very interesting, and I look forward to join the session with you guys in the next week. Okay, thank you and good night.